So this is Math 331, Lecture 18. What we're going to be doing today is we will be continuing with the problem from last time about how to divide up the number 100 in terms of a sum, and we want to maximize the product. If you want to write 100, or more generally, let's just write some number s as x1 plus xn. And initially, each xi will be a positive integer. We will then remove that condition later, and we've talked about why this is a natural condition to have. If we allowed the x's to be negative, then we could make the product arbitrarily large. So we want to maximize the product of the xi's. Anybody have any thoughts as to what might be best? Or what might be a bad idea? Yes?
Take the log.
So one thing is you could take the log, and then you would have a sum. And now the condition, unfortunately, is that the sum is supposed to be, so this may be the one time all year where we don't take the log for the product. Because then this condition becomes painful if we take a logarithm. And then the constraint that these are in the integers, when we take the log, becomes painful.
I thought you said give bad ideas.
Oh, bad ideas. Oh, I'm sorry. Then yes. Yes, we can. Well, what we will do is, unfortunately, we do not have like Major League Baseball live reviews with New York City, so I can't have it checked. But we'll check the videotape later today to see if I said worse ideas, bad ideas. So yes, a bad idea would be to take the log. This is probably the only time that's a bad idea.
Just take like one term.
Yeah, take one term. So if we take m equals 1, that yields us as the product. All right, can we do better? What might we try?
52s.
52. So we could take. Okay, so that's doing part down. Each xi equals. Okay, so this is actually doing the case when n was 100. Each I equals 2 yields 2 to the 50. So one possibility is breaking everything all the way down into 2's. And clearly this is going to be much better than just having one term. The question is, what's the sweet spot? So can you give me anything that's a bad idea? This would be a bad choice for an x.
All ones.
All ones. So each xi is greater than or equal to 2. Anytime you have a 1, you're not going to help the product. You could just have something gobble up the 1. Okay, good. So we know we're never going to use the 1. What else could we do? I was going to make it into a paper airplane. My son found a really good design. Yes? Okay, yeah. So we don't want any of the x's to be 1s. Can you give me an upper bound? What would be a really bad number to use for an x? I'm sorry? 100. Why is 100 bad? Well, but again, we're not trying to do the general case of s. I agree with you that 100 would be a bad idea. What could we replace 100 with that would increase the product? 1550. Or perhaps an easier way of doing it is 98 and 2. So if we had 100, we can replace it with 98 plus 2, and this has a higher product. Right? What if we had 99? What could we replace that with? 97 plus 2, and it's still a higher product. So how much time do we need to fill up? So we can get all the way down to 5, and we would replace that with 3 plus 2. What about 4? It's the same. So would you like to replace the 4's with 2 plus 2? It's sure. Why? I think it's actually a really good thing to replace it. Because now we know I only have 2's and 3's. Otherwise I could have 2's, 3's, and 4's. So each xi is, so now we have each xi is in 2, 3. That's a huge advantage. Okay, making progress. So it all comes down to, we have some number of 2's and some number of 3's. So you could write it as, you want, 2 times alpha plus 3 times beta to equal s, and then maximize 2 to the alpha, 3 to the beta. So it's one way to proceed. But I think we can do this without going into such great detail. What's the key observation?
You only have one three. Well, at most one three.
Okay, so you're saying you want to have more 2's than 3's.
Yes.
So you need a way to compare 2's and 3's. Oh, okay, so somebody just, some real dispute here. You look like you're about to take him down. No, he's just finally back in class.
Says 6 is 2 plus 2 plus 2, which multiplies to 8, and 6 is 3 plus 3, which multiplies to 9.
I thought 3 plus 2 is 6.
I'm checking the prereqs for the. Okay, it does say algebra is a prereq for the course. Not abstract algebra, just regular algebra. So if you multiply 2 plus 2 plus 2, if you multiply the 3 2's, you get 8. If you multiply the 2 3's, you get 9. So whenever you have 3 2's, you would always want to replace it with 2 3's. And so, in fact, we don't need to do any of this. It's going to just be 3 to the 32 times 2 squared. That will be the maximum product. We have 33 3's and a 1 left over. That 1 takes a 3 and converts it to a 4. The 4 then becomes 2 2's. So this is the best you can do. And it might seem that initially you want to have as many 2's as possible, but the 3's beat the 2's. Okay. Let's now look at what we would do if instead we allowed ourselves to assume that the x's were just real numbers. So E is going to come into play. You know it's a good day when E or pi emerges somehow in the lecture in a natural way. And this is going to be a justification for why for some things base 3 is actually better than base 2. For storing information, base 3 has an advantage. In terms of writing code and binary searches and whatnot, well, binary is better than ternary search. So let's generalize. We'll generalize. I think that's still in focus. Yes. Okay. So we will have now S is going to be x1 plus xn. Each xi is now just strictly greater than or equal to 1. We're not going to assume integer. Do we have any thoughts about upper bounds for the x's? How large could one of the x's be?
S.
Could be, it can't be larger than s. But for instance, would I expect to have one of the x's be 7?
No.
No. Why not?
We know 3 is better. Or
Why? Well, how did we get rid of 7 a moment ago?
3 plus 2 plus 2.
3 plus 2 plus 2, or even easier, just 5 plus 2.
Oh, yeah.
Right? So we can eliminate 7. We could also eliminate the square root of 17 by square root of 17 minus 2 plus 2. So we know from the same argument as before, we get 1 less than equal to xi less than equal to 4. Same analysis. So we're in some nice compact region. Now the difficulty is we don't know what n is. So what we're going to do is fix n, find best, then vary n. So we're going to do it in 2 stages. So if n equals 1, it's not that bad. You just take s. Right? If n equals 2, I claim we've seen this already this semester. It's the Farmer Brown problem. If n equals 2, I'm giving you basically a semi-perimeter or perimeter, and I want to maximize the product. So we know x1 equals x2 equals s halves. Right? That when we had 2, the best we could do was the rectangle that was a square. So what do you conjecture is true for n? What would be your conjecture? Yeah, they're all equal. x1 equals xn equals s over n. So how many of you have taken real analysis? How many of you have not taken real analysis? Okay. There is a beautiful theorem in real analysis that says if you have a continuous function on a closed bounded set or on a compact set, it attains its maximum and minimum value. I have a closed bounded set. Each xi is between 1 and 4. I have all the endpoints. This is on some n-dimensional box. The function will attain its maximum and minimum value. If you know that, it's not so bad. Imagine not all equal. Then without loss of generality, x1 does not equal x2. So you would have x1, x2, x3 through xn. Replace those with what? What can I replace those with that will increase the product? Not x2 and x4.
Replace each with x1 plus x2 over 2.
Yeah, replace each one with the average. Because remember, whatever I'm replacing it with, it has to sum to x1 plus x2. It has to have the same sum. But now we know that if I have a fixed sum, the maximum product is when they're both equal. So if I now do this, I've increased the product. So now the question becomes just how much rigor and detail do you want me to do for this? So this proves that if you ever have two components that aren't equal, we can make it larger if we replace those two components with their average, and we can keep iterating this. The problem is, how do you know that the process will terminate and that you will have a maximum? So do people want to try to make this more rigorous, or are people happy to just say, there's going to be a maximum, just keep doing this? If you ever have things that aren't equal, contradiction. So if you're willing to assume that there is a maximum, which makes sense for a continuous function on a closed bounded set, then if there were ever two components that weren't equal, you could make it larger. That violates this being the maximum. You could also try to do it with Lagrange multipliers. We have our constraint equation. The sum is equal to s, and we want to maximize the product. You could do it with Lagrange. Okay? This is enough detail for people. We're willing to. Okay. So now we know that the maximum is when they're all true. So we have now proven the conjecture. Okay. So now we will create a new function. F of n is s over n to the n is e to the n log s over n. This is going to be the maximum product when we have n pieces. What should we do now? This function is only defined on the integers. You can't take the derivative of a function that's only defined on the integers. Right? For each n is the number of pieces. So what function should I study? I need a function of a real variable x. What should I look at? I want a function that will reduce to this when x is an integer n. So I can't use calculus here because this function is only defined on the integers. I need to extend the function to other real values. What's the natural way to extend? What should I have f of x equals?
Same thing.
Yeah, the same thing. So just tell me what to write.
E to the n, or
E to the
x log s over x.
Yeah. Just extend the function. To the x. Extend it everywhere. This function now agrees with this whenever x is an integer. But now I can use calculus for this. And then the hope is that if I can find the value of x that gives me the optimal here, then the real optimal will be close to the integer optimal. So this was the idea we were talking about before, passing from the real optimal to the integer optimal. And we talked about the knapsack problem, where you can't do the discrete things. You can't take some of a can of soda.
How do we know that the continuous solution will be close to the
We don't. Yes. And so while I was willing to just wave things and say, come on, can everybody just agree that this has a maximum? For this one, I will prove it. All right. So the first is, how do we find where this has its maximum and minimum? What do we do?
Derivative, check the
All right, derivative and check the endpoints, right? So endpoints are not the maximum. If you take x equals s, you're going to get a product of 1. And if you take, if you take x equals s, you get a product of 1. And you take x equals 1, you get a product of s. So not going to be the case in those situations. So the endpoints clearly are not going to be the winners. So we need to take the derivative. Now when we take the derivative of this, what's nice is you have the exponential, then times the derivative of the argument. But we're trying to set the derivative equal to 0 to find the critical points. I don't actually care about this part because that part's never going to be 0. So I'll get the derivative, it's just my function again, and now I need the derivative of x log s over x. So I get f of x, and then when I take the derivative, I get the log of s over x plus x, and now the derivative of log of s over x. Well, that's the log of s minus the log of x. The derivative of log of x is 1 over x, so I get x times negative 1 over x. So I get f of x times the log of s over x minus 1. Therefore, s over x has to equal what? So I want the log of s over x minus 1 to be 0. So what does s over has to equal? I'm sorry? E. At the critical point, which means x is equal to s divided by e. So each piece is of size roughly e. That's the best you can do. Now, unfortunately, it is extremely unlikely that s is going to be a multiple of e. So this will give you the real optimal, but it will not give you the integer optimal. What's nice is I can use this as an opportunity to talk about Calculus 1 when I was a student. So when I was a student, calculus was taught a little bit differently than when you were. We didn't have access to these fancy graphing calculators or programs like Mathematica. We actually had units on curve sketching, where you taught how to curve sketch by using inflection points and first derivatives. How many of you were taught that? Right. More than I was expecting. Excellent. So let's sketch it a little bit. Here's my function f of x. Here's my function f prime of x. And for this one, I don't actually need f double prime. So the key points here are x equals 1, and x equals s, and x equals e. When x, or is it s over e? I guess it's s over e. What is the first derivative at s over e? It's 0. What if x is less than s over e? If x is less than s over e, what can you say about the log of s divided by x? So x is less than s over e. So they give it as s over 2e. So it's going to be, what are we going to get?
Positive.
Yeah, we're going to get something positive. This whole expression is going to be positive. So if s over x is greater than 1, if s over x is greater than e, then this is going to be greater than 1, this is going to be positive. So the function has positive first derivative going all the way up to s over e, at which point the first derivative now becomes 0. Once x is greater than s over e, this number here is now less than e. So its logarithm is going to be less than 1, so this is going to be negative. So the first derivative is now negative. So this gives you some idea of curve sketching. If the function has first derivative that's positive up to here, and then negative beyond here, what does the function look like? Yeah. The function has to look something like that. Yeah, I don't care about inflection points or anything like that, but I know the function has to look like this. Well, if the function looks like this, if this is the real maximum, then the integer maximum, I just have to check the 2 points immediately to the left and the right. And this allows us to pass from real to integer max. You typically cannot do this. But this is an extremely powerful technique. The curve sketching ideas, that's all we really need. This is in some sense the first derivative test from calculus. If the first derivative goes positive to negative, then you have a maximum. Okay, so this is a really good problem. I'll try to send you a link about why this tells you that base 3 is more efficient for storing things than base 2 in terms of applicability and availability. But I like this problem where it just reviews a lot of the techniques for calculus. We have to do, in some sense, 2 optimizations. We first fix n, optimize, and then we vary n. We have to deal with how do you pass from a real maximum to an integer maximum. And there was some questions about trying to do some optimization problems in the class. All right. Any other questions on this? Okay, so we're good on this. We did the quadratic polynomial with ABC and how we did this for coding, right? And now we're going to move to Hamming codes. So there's a couple of different ways to present Hamming codes. I'm going to do it slightly differently than I think is on Wikipedia, fountain of all knowledge, source of all wisdom. I think this approach just makes it a little clearer what's going on. And again, mathematically, it doesn't really matter which approach you take, but in terms of when you're programming things to implement, it's sometimes more convenient to code it one way rather than another. In terms of which data positions do you want to be for information, which data positions do you want to be for checks. So the whole idea of Hamming codes is these are error detection and correction. So not only do you tell me that a mistake was made, you actually fix it. And again, Hamming was, I think, low person on the totem pole. His programs ran over the weekend, and he would come in on Monday and see that it only did 14 lines. And was just furious that the machine can tell me that there's a mistake. Why can't it fix it? And we talked about scanners before, barcode scanners at supermarkets or Walmart or stuff like that, where if it misreads a digit, it uses the checksum. Okay, so the first was the tell me 3 times. I mentioned the Philip K. Dick story, Minority Report. So you transmit 1, 1, 1 or 0, 0, 0. And if you receive anything else, you go to whichever word is closest. So another way of writing this is I have 111 up here, 0, 0, 0 over here, and then I've got 110, 101, 011. These are all 1 unit away from 111. Down here I have 100, 010, and then 001. These are all 1 unit away from 000. And we are measuring distance by how many bits differ. This is now called, I believe, the Hamming metric in honor of Hamming. Just look and see how many bits are different, and that tells you how far apart words are. It's a good way of seeing how far apart things are. How far apart are these words? These will all be 2 apart. How far apart are these from here to here?
3.
Those will all be 3 apart. What about from here to here?
1.
So from there to there, it'll be 1 thing apart. So if I actually wanted to draw everything nicely in terms of how far the distances are, we get a little bit complicated. But I know these words are all 1 unit away from here. These words are all 1 unit away from here. And so if I take a message, these are my code words. And whenever you receive something, everything is either a code word or 1 away from a code word. And so if I receive any of these 3, I correct to this. If I receive any of these 3, I correct to this. Is it possible that I received 000 and I meant to get 111? Yes. Hopefully your transmission error rate is small. So then having 2 or 3 errors is damn small. And then we talked about the Seinfeld episode, The Opposite, where George Costanza realizes that every decision he's made in his life is wrong. And as long as you live in a world of just binary choices, if you know everything you do is wrong, let's say you're taking a true-false test, and you know you're going to get everything wrong, great, get everything wrong, and then flip, and you'll have everything right. So there's a lot of things that are, it's p times 1 minus p, and that's maximized at p equals a half. That's where things are going to be worse. And when you're 50-50, you have no idea if you're correct or incorrect. There's no information there. But if you can be completely wrong, that is the same as being completely right in a binary world. So in this situation, we really only have 1 piece of information among the 3 digits. So the code is extremely inefficient. Only 33% of the digits are really the message. The other 2 bits is for the error detection and correction. So only 1 of 3 is data. This sucks. This means the majority of your message is redundancy. It sucks a lot less than when I was younger. Why? Why does this suck a lot less than when I was younger?
You couldn't transmit information at all?
I'm sorry, you have to speak into the good ear, please. We could transmit information. We had smoke signals. We had carrier pigeons. We had Morse code and telegraph. No, so we could transmit information. But back then, the bandwidth you had was really bad. How many of you know about Napster? So there were a lot of college campuses where OIT had to do, I gotta be very careful, actions against students using Napster. Of course they didn't like people pirating stuff, but it was taking up a significant amount of bandwidth. Now things are much better, so a lot of these things you can ignore a little bit. You can afford a little bit more inefficiency because we can transmit so much more, so much faster. You no longer have those long dial-up modems where you have really restricted amount of information. So this is not as bad, but it's still an issue. And if you can do better, you'd like to do better. So what I want to do now is I want to show you at least a small improvement. And then as time permits, we'll talk a little bit about what do you expect to happen in the limit. So when you look at this method, one data point is not great. What if I tried to expand this? Do I think I can do better than 1/3? Hopefully. How much better? In the limit, do you think I can have almost 100% of my message be information? And if so, how many things can I correct? So right now, we're constructing codes that can correct 1-bit error. You can construct codes that will correct 2-bit errors, but that will cost you more, and you'll have less information. So the first thing is we are transmitting 3 pieces of information. Does anybody know why 3? It's really hard with just one data point.
It's odd.
It's odd. So one thing is 3 is odd.
If you do 2, you can't tell what the error is.
So if you did 2, you can't tell what the error is. What do you think the next one we should transmit should be? How many pieces?
9.
Nope.
5.
Nope. You're close. It is between 5 and 9. 7, of course, 7. All right. Anybody want to give me the next one?
15.
15 is the next one. Excellent. What's the next one? 31. One more. 63. Right. These are 1 less than powers of 2. Let's look at the tell me 3 times in a better way. Okay? And again, I think this is a much better way of presenting the material. I'm going to add some parity bits. I'm going to add a parity bit here. I'm going to add a parity bit here. And this parity bit will be the sum of the entries in this row. And this parity bit will be the sum of the entries in this column. If instead I had a 0, I would have this. Right? Now, imagine you receive the following. Because this is a 0, that should be a 0. So now you know there's a mistake in the first row. You also know there's a mistake in the first column. Oh, okay, I know where the mistake is. This is the mistake. And so these two allow you to uniquely determine where the mistake is. What if you receive this? Well, this row looks good. This column looks bad. So there's a mistake in the first column, but not in the first row. The mistake is the parity bit. So this is a really nice way of, I think, conveying what you're doing. What do you think we should do now for our 7? Where should the data be? So we need 4 data, 3 parity bits.
A square of data.
So square of data. x1, x2, x3, x4. And this will be x1 plus x2 mod 2. So if the sum is even, I have a 0. If the sum is odd, I have a 1. This should be x3 plus x4 mod 2. This is x1 plus x3 mod 2, and then x3 plus x2 plus x4 mod 2. So now, if there's a mistake in this row and a mistake in this column, it will uniquely specify where the error is. This is wonderful.
I thought we could only have 3.
Yeah. I was hoping you wouldn't notice that. All right, so there's a slight issue. But, baby steps. This at least gives us 50% of the message's information. Of the 8 bits, at least half of it is information. Do we need all the parity checks? Which one don't we need? Any one. Because if you add this parity bit plus this parity bit plus this parity bit plus this parity bit, what must you get? 0. Because if you add them all, you have x1 twice, x2 twice, x3 twice, and x4 twice. So you actually don't need all 4 parity bits. So with loss of generality, you can eliminate one parity bit as known. Known from others.
Wait, so is this why we were maximizing the product given the sum?
No.
No?
Nope, sorry, nope. Unrelated, the lecture's not that
Because
good.
like you're maximizing the amount of data you're storing, and like that's like the amount of data you're storing is like n squared, where that's like the size of the grid.
Right, so it's somewhat related to that in terms of how much of the message is useful. And so absolutely there's connections like that. It's not directly connected. I wish it were. I mean, I could then get one of these medals for lecture of the year. I've got spot. I can move some of my Legos and Rubik's cubes and make some room for it in my office. But there'll be some connections. But we don't need to waste a parity bit here. It's convenient if you want to put it there, but you're then decreasing your efficiency by a significant amount. This breaks 50%. So a majority of your message, 4 out of 7 bits, is information. Okay? Yes?
So sorry, we're saying that the parity bits uniquely determine where like any mistakes are? But
Yes.
Are we assuming that the parity bits themselves don't have
No, the mistake could be in the parity bit. So imagine imagine that this plus this is not equal to this mod 2. I now know there's a mistake in the first row. But imagine these 2 columns are correct. Then I know the mistake has to be in the parity bit over here. If I have a mistake here and a mistake here, then that uniquely specifies x1. If I have a mistake here and here, it uniquely specifies x3.
Okay.
So these allow me to detect where the mistake is. And the mistake could be in the parity bit.
If you have a mistake in only the second row,
Okay.
and everything else is right,
Mhm.
then you wouldn't know if it's x4 or the parity bit, right? It's 50-50.
Well, because I know this plus this plus this plus this is supposed to be.
But you don't have the bottom right.
I don't have this.
Oh yeah, you can calculate.
But I can calculate it.
Okay.
Right? I know what these 3 are. And so if I have an odd sum, I put a 1. If I have an even sum, I put a 0. So I actually do know this. That's why I'm writing known from others. So you can uniquely determine where the error is. So this will allow you to correct one mistake. Okay. One of the big things you always want to do is you want to get a sense of how good is something like this as we go further and further and further. Okay? So what we would really have in general is we're going to have some kind of block here. Before we had a 1x1 block, a 2x2 block. So now we could have maybe an n×n block here. Right? And then we have some parity bits here and some parity bits here. And what you can see is that the number of pieces of data is going to be of size n squared. So data of size n squared, parity bits. So how many parity bits do we have? 2n minus 1. So in limit, 100% is information. So you can have your message as much content as you want. The problem is now, of course, is that if you have very big messages, then you become more and more likely to have a parity error somewhere. With a low probability, with enough occurrences, something unlikely will happen. So there's trade-offs as to what size do you want. And you could even have more codes where you allow yourself to correct 2 errors or 3 errors. So again, part of what I'm trying to do in this class is give you a sense of what's out there. And show you how, if you look at problems the right way, you can often do tremendous things. And frequently the limiting behavior is not what you might expect from the small values. It can be extremely misleading. When you look at the tell me 3 times method, it looks like it sucks. Now, this is not powers of 2, right? So this aligns with the Hamming method over here, but is not quite the same as the Hamming method for other things. So I am not trying to do the best, most efficient thing possible. I'm just trying to show you something that's out there that might be better than you would expect and is really easy to do and implement. Because again, if you only have one mistake, it will affect, if it's in here, 2 spots over here, and that will uniquely determine. And if it only affects one of them, then you know it's the parity bit that's wrong. Okay. Any questions on this? Right.
It reminds me of the law of large numbers, where
Mhm.
the mean goes up
Yeah.
continually and the standard deviation is rooted.
Yes. And so with higher and higher probability, you are very confident percent-wise of where you are. So if you look at EM molecules, it is possible that all the EM molecules will be in your half of the classroom and I will not complete the lecture. Fortunately, we gave out the exams before class began, so good. It's unlikely. And so the fluctuations is going to be of size square root of n. Anybody know roughly how many EM molecules we have in the room? Within a few orders of magnitude.
2 to the...
No. You can't say it is 2 to the. That's the wrong way to do it. You need to know some chemistry.
10 to the.
10 to the what?
23.
10 to the 23 is Avogadro's number. It's the number of things in a mole. Do you think there's just 1 mole in here? No. Do you think there's more than 10,000 moles?
Yes. No. Maybe.
Yeah. So this is the question of, do we have any rough idea of what's going on? I think 10,000 moles is probably more than what we have in here.
Things a mole.
Oh, we can do like or
10 to the 23.
pressure and stuff.
To be safe, I would say if we go with 10 to the 28, I think we're definitely within 5 orders of magnitude. As an aside, one of the best quotes I ever heard in my life was trying to explain how energetic some radiation was. And they said, imagine a lead shield stretching from the sun to Pluto. It could go through that. I was like, okay, that's something I can picture. I'm in the dentist's office, and I have this lead shield going all the way to Pluto, and it's still going to get through it. Okay, let's look at the checkerboard problem. So let's assume you have n is m squared. This is going to be the easiest case. So now we will do m by m queens down here, and we will see how many things are killed. So these m rows are all, these m columns are all killed. These m rows are all killed. And then these diagonals are all killed. In life, do trivial estimation if it works. I don't care if I double count a little bit. How many things do I lose from the columns? I'm sorry? How many spots are killed from the m columns? So,
sorry.
So this whole board is n, which is m squared. So we have n squared elements of the board. And now we want to see how many things we kill. So how many things are killed in those m columns? I'm sorry? nm. Right? How many things are killed in these rows? Same. And again, I'm double counting this, but that's of size m squared, which is insignificant next to n squared. Because n squared is m to the fourth. So I don't really care about double counting that. Now let's look at the diagonal. How many diagonals do we have? Maybe m times 2m, maybe 2m plus 1 diagonals, maybe?
I think it's linear in M.
It's linear in m, but we have m going up to here, and then we have maybe m minus 1 more. I think if we do 2m plus 1 diagonals, that should be safe. Right?
Do we have any shared diagonals? What if it's not being shared?
I think there could be some short. I'm just trying to be safe right now.
Well, they're like.
If I do 2m plus 1, I'm safe.
2m.
I'm safe. It's lower order terms. I don't care about lower order terms. They're not like my children or my students. How many elements do I have on each diagonal, upper bound? N. Right? Let's just be crude. So now this is going to be n squared minus, I've got 2m plus 2m plus 1, so it's going to be 4m plus 1 times n. So this is going to be n squared minus 4 square root of n plus 1 times n. So this is of size n to the 3 halves. It's significantly lower order than this. So we look at the fraction that's safe. It's going to be at least n squared minus 4 square root of n plus 1 over n divided by n squared, which goes to 1. And that's why we don't have to worry about being careful and being accurate. It doesn't matter. You're going to be talking about terms of size n to the 3 halves. Now, if I wanted to calculate what is the limiting behavior, if I throw away the main term and I look at the fluctuations, absolutely would then need to do that. And again, this is just one configuration. But this tells you that in the limit, you can get 100%. And what I love about this problem is this is quite surprising when you look at the small values.